Today, I am going to talk about a new group of smart polymers, and these are active smart polymers. So, there are many such polymers which behaves very similar to the piezoceramics or magnetostrictive materials that we have seen, in the sense of both from the direct effect as well as from the reverse effect point of view, and these polymers are very useful for us. Why? Because the elastic modulus of a polymer is much less in comparison to the ceramic or the metallic counterparts. So, as a result they are more compliant. So, you can give actually very flexible shapes by these polymers, and then you can use them as integrated sensors or as integrated actuators. So, our intention is to look into the polymers, those subgroup of polymers which shows some amount of smartness, that is both in terms of the direct as well as in terms of the reverse effect. Now, IPMCs or this group of active polymers are specially important because of the demand of developing new robotic locomotion systems which would simulate the animal locomotion. In fact, if you look at the development of robotics with respect to various types of robots which can simulate or biomimic the animal locomotion, then the first in the group are something like the quadruped stair climber titans. So, these are actually many leg kind of a robot, and then there is this snake like robot ACMR5, and also later on people developed bipedal walking robot. The important thing is that in all these robots the actuation, for example, in this biped is achieved through the use of conventional motors, but motors are heavy, motors are more power consuming, and they have backlashes and other problems. So, people started thinking, can we not replace these motors by something like artificial muscles. So, replacing motors by artificial muscles is something that triggered actually the development of active polymers by artificial muscles. Like these regions, you develop muscle system with the help of polymers which can substitute the motor based system. So, hence today we will talk about some of these smart polymers. First we will define ourselves that what is an active smart polymer. We will then talk about the classifications of these electroactive polymers, and then we will mostly talk about the applications of these smart polymers. So, the first thing is that what is an active smart polymer? The polymers that would respond to external stimuli by changing shape or size are known as active smart polymer. So, which means that it is mostly the reverse effect that has been kept in mind, that you are giving some external stimuli and the polymer is changing its shape or size. Of course, the other way, the direct effect is also available in some of these polymers, and we will talk about it whenever this polymer will come into the discussion. Now, active polymers can be divided into two subgroups. In one group, the response can be anything other than electrical and of course mechanical. So, for example, if it is pH, if it is magnetic field or light for that matter, like polyanionic cellulose PACs, and there are many such active polymers. I will show one example soon. So, these polymers are known as active polymers, simply active polymers, as they respond to input stimuli which are generally non-electric in nature. Now, electroactive polymers on the other hand, as the name suggests, that they respond to the change of electrical input, and hence they are known as EAP or electroactive polymer. Now, given a choice, which one would we prefer? Of course, we would prefer the electroactive polymer, because it is easier to control such a system. To control the movement of a system with the help of a magnetic field generation, or with the help of a pH change chemically, or with the help of light intensity, is still not, the technology has not developed up to that extent. On the other hand, to control it electrically, it is much better. So, one of the examples I told you in the terms of a only active polymer is this light based response of the azobenzene groups. These azobenzene groups actually contain this double bond of nitrogen. Now, what happens under visible light, as you can see that this is the double band of nitrogen here, as you can see. Now, under visible light, these double bonds go to a cis conformation. So, the moment you put light on this, they go to a cis configuration, something like an angular configuration. So, that is why we say that it gets bent, and under UV light this goes to the trans configuration. So, this is under UV light, which means they remain straight. So, it is straight under UV light, and under natural light it is bent. Now, if you develop a system like that, as you can see, and then successively you apply the UV light and plane light, then what you can do is that you can bend it, you can straight it, bend it, and like that the bending and straightening sequence, you can actually use it in terms of locomotion of a system. So, this is one of the supposed to be a very active smart polymer which is coming up. So, this is one of the uses of an active smart polymer. Now, let us come back to the focus of electroactive polymers, which I said will be more useful. EAPs will be more useful in terms of the development of actuators and sensors. So, if we compare electroactive polymers with the shape memory alloys, which I will be talking about in the next lecture, and electroactive ceramics, where are they? The most noticeable thing is that the strain that it deforms is greater than 10%, which is much greater than any one of the other two categories. What it means is that you can make actually very large deformation in this system. The force on the other hand, stress for example 0.1 to 3 MPa, which means whereas this is very high, this is very low, the force availability. Reaction speed is about microsecond to second. Electroactive polymers are generally quite fast, but it varies. Density wise, once again the density is low. Drive voltage is extraordinarily low, 2 to 7 volts. Compare that with electroceramics 50 to 800 volts. The power consumption is also very low, milliwatt range. Compare that with electroceramics or SMAs, which is in the watts range. And the fracture toughness is almost absent, it is very resilient and elastic. On the other hand, the electroactive ceramics are very fragile. So, from many such points of views, we can see that electroactive polymers are going to be much more useful for us in comparison to any other smart materials. Now, electroactive polymers itself can be subdivided into two subgroups. One is called electronic electroactive polymer, where the change in the polymer is driven by the change in the electric field or Coulomb forces. For example, you think of the PVDF, I already said, piezoelectric material, that is one of the electronic electroactive polymer, or dielectric EAPs, electrostrictive papers, ferroelectric polymers, or liquid crystal elastomers. All of them are they respond by the change of the electric field. On the other hand, for ionic electroactive polymer, this actually responds due to the mobility or the diffusion of the ions. For example, ionic polymer gels or ionic polymer metal composites, we shortly call it IPMCs. There are many IPMCs available like Nafion from DuPont and Selemion from Asahi, Japan. Then conducting polymers and carbon nanotubes also come into the category of ionic electroactive polymer, where the changes happen due to the mobility or diffusion of the ions. Now, let us compare between the EEAPs and the IEAP, that is electronic electroactive polymer and ionic electroactive polymer. The first important thing is that electronic electroactive polymer needs high actuation voltage, something like greater than 150 volts per micrometer. On the other hand, IEAPs require low driving voltage, something like 1 to 5 volts. Secondly, electronic electroactive polymers have high energy density and rapid response time. On the other hand, ionic electroactive polymers are slow, but the amount of deformation is more and it performs better under wet condition, because I told you that it is the mobility of the water in the ionic form that actually creates the deformation. So, if it remains moist, more amount of ions of water will be going towards a particular size, and as a result there will be more deformation in the system. So, there are many applications of it, as you can see that people have thought of using it as a dust wiper, particularly for space applications. So, today's wiper, how does it move? You must have seen that it works like a rigid movement. So, because of that rigid movement, it swipes a curve, and if you have one more of this type, then that swipes another curve. But then there will be some corners which you will not be able to reach by either of them, and those corners if you have on the other hand a dust wiper which can actually vary its length, if you use such dust if you use such kind of a long wiper which can vary its length, then you can actually go from one corner to the other corner with whatever work volume you wish, it can go very nicely. So, that is what IPMC is very good for, that kind of a system. Also for handling the samples, just like our fingers, it can deform to a very high extent for handling of the samples. So, if I try to kind of bring all these applications together, we will see that one good application is in terms of mechanisms. It can be used for lens controlling, for mechanical lock, noise reduction, for flight control surfaces or anti-G shoots. So, for all sorts of mechanisms you can use this. You can use it for robotics, like I showed you the example of the walking robot etc., biologically inspired robots, toys and animations. You can use it for human machine interfaces. Towards the end of this lecture, I will show you one such application, tactile interface, okay, artificial nose, things like that. Then you can use it for planetary interfaces, like I told you that you can use it for that wiper or gripper or cleaner wiper or shape control of Gossamer structures, like that. There is a good use of this material for medical applications. For example, it is used for biological muscle augmentation, okay, that is one. Then miniature in vivo EAP robots for diagnostics and microsurgery, chatter steering mechanism, tissue growth engineering, interfacing neuron to electronic devices, active bandages, etc. You can also use such a system for liquid and gas flow control, controlled weaving for garments and clothing, then for MEMS and for EM polymer sensors and transducers. So, it really has a very broad field of applications. Now, how does it look like? This is typically a ionic, I should say this is an ionic electroactive polymer, that is IEAP. So, what you have here is this is typically Nafion, for example, would behave like this Nafion. So, you have this polymer here, the ion exchange polymer, and there are these depositions of particles on it. Now, these particles, you can actually metallize the surface, with the help of an electrode. You can metallize this surface, so that you can apply the voltage to generate a polarity like cathode or anodes. Now, if you look at one of the ionic electroactive polymer, which is IPMC. So, IPMC is ionic polymer matrix composite, ionic polymer matrix composite. Short form is IPMC. If I look at the structure of IPMC, what I am going to see is that the main chain is actually PTFEs, and that is the source of its strength. PTFE is something that is used even for your applications like non-stick or things like that. So, it is very strong, and on the other hand it has some additional groups which are like sulfonate groups, which is its source of polarity. So, IPMC is basically, or Nafion is actually pre-fluorinated copolymer of PTFE and a pre-fluorinated vinyl ether sulfonate. So, there are two copolymers that are used for developing this polymer. One gives it the strength in the backbone and the other gives it the source of polarity. Now, how does this system would work? This polymer would consist of a fixed network with negative charges balanced by mobile positive ions. This is important. It has a fixed network, and in that fixed network there are these negative charges, as you can see, and these negative charges are balanced by positive ions around them. Mobile positive ions are just fixed to it. When it is subjected to DC voltage like this, what do you expect to happen? There will be then the accumulation of all the cations near the cathode. So, as a result, you can see that all the cations are coming close to the cathode, so that kind of a migration that is taking place. So, here the blue things are the fixed anions, as you can see, these are the fixed anions and these are the mobile cations. So, all these mobile cations, as you can see, they have migrated towards one side, right, towards these the negative side, and as they have migrated, what will happen is that the water molecules will move towards this side and it will create a hydrophilic expansion. That is why the whole thing has got bent. So, the polymer matrix will bend towards the anode side. This is your anode side. So, as the cations will be moving, we are going to get the bend towards the anode side. However, what will happen is, after some amount of substantial these things have there to neutralize, you will get a back diffusion of water molecules, which will cause a slow relaxation towards the cathode. That means, not everything will remain attached, little bit of after some time back scattering would start to happen. Now, the extent of this actuation of course depends on the type of the polymer, type of counter ions, presence of moisture, quality of metallizations, etc. But that is the basic principle of how an IPMC would work. Now, these IPMCs are having several characteristics. One is that large deformation, low actuation voltage and fast response. So, here what we can see is that if you build up these two electrodes and you pass a current, you are going to get this kind of a bent shape in the system. So, it will change its shape as you are going to apply the electric voltage. Something similar you can see on the Nafions here. Now, can we get only one type of curvature, only in one direction? No, you can actually, depending on the type of electrodes, okay, you can actually get two different types of electrodes like here, and then if you apply the voltage, you may get upward bending in one side and downward in the other side, and as a result you can get a bidirectional curvature. If you have more such combinations of electrodes, so you have a beam, let us say, which has more combination of electrodes. This is the top view of it. So, what I am going to see? I am going to see a wiggly motion of the system, somewhat similar to the motion of the snakes. So, you see the double curvature is really very beneficial for this kind of a system. Now, double bending in one of the typical material like Selemion, which is a generic name of ion exchange membranes of Asai class, you will see that it consists of Selemion and the left half of its top and bottom surface are coated with gold foils, whereas the right half of its top and bottom are coated with something called dotite. Now, dotite is an electrically conductive adhesive containing silver powder manufactured by Fujikura. So, as a result you will get a double curvature in this system. So, these are some of the strategies, like you coat with two different materials and then you get a double curvature out of the system. IPMC based actuators have many applications, but the major applications are in terms of single link manipulators. That means, when only one link, one single link you have, and using that itself you need to bend it enough in order to hold something and in order to transfer this thing at some other location. So, that is single link manipulation. You can of course, then use it for multi-link grippers, for vibration generation and control, for 4-bar manipulation and for biomimetic systems. IPMCs thus have versatile applications. Like as a single electrode, if you use only one electrode, then you can actually, you will see that you can actually go through this kind of an workspace. So, that is the maximum that you can cover with this type of a system. On the other hand, if you have 3 or 4 of them, then you can use it for holding something, some material from space. So, you can use it in the form of developing a gripper system. If you use 2 or more patches, then in fact you can actually manipulate a small object in the work volume, and the degree of freedom available will depend on the number of such patches, like one patch and then you have a second patch. So, you can easily make this kind of shapes, etc. You can not only that, you can also make a 4-bar mechanism using active polymer like IPMC. As you can see here, this is a 4-bar mechanism. So, 1, 2, 3 and that is the 4th link. So, with this 4-bar mechanism, as you are moving this rocker part of it, then the coupler transfers the motion and you get this part of course becoming flexible, you get a kind of a motion due to the bending of this link. Now, that workspace of course you can control by applying voltage in the system in an active manner, so that you can control the workspace that it can generate. One of the IPMC which is coming up in a big way is known as the gold polypyrrole IPMCs. So, that is good in the terms of lightness, corrosive, anti-corrosive properties, etc. This is what I told you is a fascinating example of tomorrow, that this robot here has lips, artificial lips, which is made of IPMCs. What it does is that through its vision, it is scanning the lips of this person, and then what it is going to do is that it is going to, so it is scanning the lips here, it is scanning the lips here, and it is going to change its shape of these lips, so that it can mimic the master system. So, tomorrow's animations can be based on this kind of biomimetic systems. So, this is where we will end today's lecture, and in the next lecture we will talk about shape memory alloys, we will give an introduction. Also, we will talk about one and two way shape memory effects. Thank you.